This video will be on section 5.5, computing definite integrals. So the first thing, we'll start with the fundamental theorem of calculus, which actually tells you how to compute definite integrals. Then we'll practice doing definite integrals. We'll also practice doing definite integrals with substitution. One interesting application of computing definite integrals is figuring out the average value of a function. But this is different than figuring out, let's say, the average cost back when we did that in chapter 2, because the way our cost functions work is it tells you the cost of that many, not the cost of that one. So normally a function tells you, if it's dealing with a cost, to relate it, it would tell you the cost of that one. So when you say like the cost of the 100th item, and you want to find the average value over a range, you can't just divide by 100. But we'll see that's very much related to definite integrals. It's just one little extra step. And then the last thing is using definite integrals in word problems. Pretty much all of section 6.2, the last one we do, is going to be using definite integrals in our word problems related to business. And so this can be a little preview on how you deal with definite integrals in word problems, set up the problems and everything. But the first thing, the fundamental theorem of calculus, recall from last section 5.4 that the Riemann sums, those were the rectangles, the areas of the rectangles. We tried to approximate the area between our function curve and the x-axis with these Riemann sums. So the areas of the rectangles. And we kind of saw, I showed you, that the more rectangles you make, the closer your area gets. So you have less overestimation, you have less underestimation. Well, the idea is if you take the number of rectangles to infinity, it'll give you the exact area. But as we've learned with infinity before in this class, is that infinity is not a real number. You could not actually plug that in. So the issue there would be, if we can't plug it in, how do we do it? Well, that's what the limits are for. So the reason this connects to calculus, it connects to our regular indefinite integrals, is that limit. If you work out the brutal details of the formula and the limit and everything, you'll actually see the definition of the derivative pop up, and that's how it's related. All right, but the fundamental theorem of calculus, this tells you how to evaluate definite integrals. All right, so I'll read the formal theorem with the notation, and then I'll explain what it means in words. It says, suppose f is a continuous function on the interval a to b, and let g be the antiderivative of f with c equals 0. So remember, when we deal with antiderivatives, we always have that plus c. When you deal with definite integrals, when there's numbers on here, you don't have to write the plus c anymore. The reason why is when you plug in the numbers, they'll actually cancel out. So no matter what you choose for c, it would cancel out. That's why it's easiest just to forget about c when you do definite integrals, say it's 0. All right, but then it says the definite integral from a to b of f of x dx equals g of b minus g of a. And so what this says in words, the way we're going to relate it is what we're going to do. We do the antiderivative of the function inside. So this is just what we did before. But like I would just mention, we don't have to write the plus c. And then what the rest of the formula is saying, this b and this a, it's telling you to plug in the top number to that function, subtract, and then plug in the bottom number a. But you have to make sure you do the top minus the bottom. If you do bottom minus top, you'll be off by a negative sign. All right, and that's the important note that I wrote before. When computing, or that I mentioned before, when computing a definite integral, you do not have to do the plus c at the end because it will cancel out. I just have an example here. You can just look and see what I mean by canceling out. So let's say we wanted to do the definite integral of x dx from 0 to 1. When we integrate x, we get x squared over 2. And from before, we have our plus c, saying maybe at this point I didn't tell you that you didn't have to use the plus c, so you still need to technically use it. Now what this vertical bar here is, this is called the evaluation bar. It's a good way to keep track of your work. All right, and this vertical bar means I'm going to plug in the top number, subtract, and plug in the bottom number to the inside. Exactly what the definite integral means as well. Right, but you can see the next line I plugged in 1 for x, subtract, plugged in 0 for x. And like we've seen before, whenever you are subtracting something with multiple terms here, you have to make sure you do your parentheses so everything gets distributed correctly. All right, then the next line I just simplified. 1 squared is 1, 0 squared is 0. So we have 1/2 plus c minus 0 plus c. Then the next line is just distributing the minus sign. And you see what happens here is that you have a plus c and a minus c, and those always cancel. So that's why you don't have to use them at all. You can pretend c is 0 when you do definite integrals, because no matter what c is, the problems always work out like this and you always get cancellation. And then the answer to this one, if you were asked to do this, is 1/2. Remember, the definite integral is like an area, so you should get a number. It can be negative, like we saw last section, so it can be a negative number. But you should only get a number as your final answer. All right, but that's just, an example. So I could show you how the c's cancel. If you are doing indefinite integrals like in 5.1 and 5.2, where you don't have numbers on the integral sign, then you still need to write the plus c. That rule hasn't changed. But if you have the numbers on them, you do not need the plus c. Okay. But for the main thing about this section, since you've computed definite or indefinite integrals, it's just a matter of doing that and then plugging in your numbers, which is usually the easy part. So we've really done the hard part before. All right, so we want to evaluate the following definite integrals. Once again, the first step is to integrate as if the numbers weren't even there. All right, and this is something we can integrate all at once, because it's, you can separate into the two different integrals because of the minus, but we can integrate it all at once because we could do each part individually. When we integrate a number, 3, we get that number times x, then minus, and when we integrate 3x to the -2, the 3 sticks around. We do our power rule, which means we add 1. -2 plus 1 is -1, and divide by the new power. Right? But since we have our numbers on the integral here, I'm not going to write my plus c. Instead, I'm going to do my evaluation bar from 4 to 6. Now, because you are plugging in numbers, it might be better to get rid of the negative exponents and then plug in. So I'm not going to actually plug in yet. This part's optional, but I like to put parentheses around the entire thing. So you kind of separate when you plug in the top and bottom. But to simplify the second term, the minus on the top and bottom cancel to give us a plus. And then the x to the -1 goes down to the x to the 1 on the bottom. Right, so all I did in this part was simplify. I didn't do any calculus or anything like that. Right? Now, if it was the old problems, we would be done. We would just write a plus c here instead of this bar, and we would be done. But it's not the old problems. We have the new problems. Now we do what the evaluation bar says. We're going to plug in the top, which is 6. So we got 3 times 6 plus 3 over 6. Subtract and then plug in the bottom. 3 times 4 plus 3 over 4. And remember that parentheses. That's why I like to write it here, is if you write it here, then you'll more likely to remember to write it there. All right, well, we plug in the top number 6, subtract, plug in the bottom number 4. Now, what I prefer to do is simplify each term and also distribute that minus sign through. Keep in mind here on the front term, the parentheses is not needed because there's no number to distribute. But we do need to distribute the minus sign through the second part. To get rid of that parentheses. But the first thing, 3 times 6 is 18, plus 3 over 6 simplifies to 1/2. Distribute the minus sign through. 3 times 4 is 12. Since this is a plus, when we distribute the minus through, it goes to a minus. And 3 over 4 is a simplified fraction. 8. Now once you hear this is a number, once you simplify this number, you have your simplified final answer. So that's all you have to do now. And you can do this all in your calculator. Yeah, just make sure your simplified answer is a fraction. Unless the homework problem says you can round. Okay. Now the reason, this one wouldn't be too hard to do by hand, but the reason I say just use your calculator if you want for this one is these problems especially, as these numbers can get quite messy, because when you do the power rule, that whole having to divide by the new power and everything creates a lot of fractions. So typically it's just easier to just type it in your calculator. So we got 18 plus 1/2 minus 12 minus 3 divided by 4. And then to change it to a fraction, hit math, frac, and we get 23 over 4. Okay. So if you graphed this, and especially with by hand, but even in the calculator you wouldn't be able to get the number. But if you did graph this and looked at the graph between 4 and 6, you would see exactly this area. So just to kind of explain it a little bit more, let's just graph it so I can explain, and you can see more so where the number came from. So we got y equals 3 minus 3x and -2. We graphed this function. I'm just going to hit zoom 6 for starters. We only care between 4 and 6. Now 1, 2, 3, x is 4 is here, and x is 6 is here. Since I can see the picture nice, I'm just going to adjust the window. So let's say from 2 to 8 instead of -10 to 10. and the y was between like 0 and 5, so let's do 0 to 6. Right, now I can't draw on the calculator, but I started it at 2, so 2, 3, 4 is about right here. Over to 6 is here. And notice that if we drew one big rectangle, it would be a rectangle with base or width 2, and the height, this is 1, 2, 3, close to 3. So it'd be a number that's close to 2 times 3, which is 6, and our 23 divided by 4 is really close to 6. So the area we got here makes sense. In general, you won't really be able to do this. We're going to have, in some problems, very messy functions. They might go up and down. They might drop below and above the x-axis. So, the integrate correctly. It'll do your work for you. You don't have to try to interpret it necessarily. But just so you can see that we are actually finding that area. I think it's a nice thing to see. All right, but for the rest, we'll just do the calculus part out. I'm not going to do the graphing. This next one here, really not much different than the first, just extra practice. We want to do the differential from 4 to 5 of 3x cubed plus 7. All right, once again, we integrate first. All right, so we integrate 3x cubed. We leave the 3 alone. We add 1 to the power of x and divide by the new power. Plus, and then when we integrate a number, it's just the number times the variable, so 7x. And because we have our numbers here, we have a definite interval, we put our evaluation bar. Right. Now this one's simplified because 3 over 4 doesn't simplify. There's nothing else to do there. But I like to put the parentheses like I mentioned. So we're ready to plug in. All right, so we got to plug in the top number 5 for x. We subtract, and then we plug in the bottom number 4 for x. And even since you're going to use your calculator, you could even do it from this stage. Type in the entire thing if you wanted. Type in the first thing, type in the second thing, and subtract it. It really doesn't matter to me how much you show here. I just need to see that you understand what this means. Plug in the top and bottom and subtract them, and then get that answer. So what I usually like to do, because the numbers in the previous part were pretty straightforward to work with, I didn't have to, but these can be kind of big. So what I usually do is type in the first thing. We got 3 times 5 to the 4th divided by 4 plus 7 times 5, at least is pretty quick, so I'm just going to write 35. If it gives me a decimal, I'm going to switch it to a fraction and write that fraction down. So the first one is 2015 over 4. Just keep the fraction as you go. Makes it a lot easier when you're at your final stage. And then the second one, I'm going to hit second enter to get back up to there, so I don't have to type it all in. We plug in x is 4, and then that 35, 7 times 4 is 28, so that gets changed. And that's a whole number, so we don't have to switch it to a fraction. Minus 220. And now, since you left each as a fraction, then you can type each in your calculator. 2015 divided by 4 minus 220. If you get a decimal, hit math and frac, and we got 1,135 over 4. All right, now you can tell from the decimal we got here, the 283, that figuring out the area here by looking at the graph would be pretty hard because, well, it wouldn't be hard, but we would spend a long time searching for it because the width of our rectangle, the base from 4 to 5 is just 1. So the height must be around 283. You might spend a long time searching for that. Right, so you don't necessarily want to try to graph and get your answer like that. It's just a way to interpret your answer with a graph, see if it makes sense. All right, so the next one looks very short and sweet. We have to integrate from 2 to 6 the function 4 over x dx. Just like before, the numbers are useless until after we integrate. We integrate first. Now for this one, if you're not as comfortable doing it right away, you can factor the 4 out. Right, you can still do all those rules when the integral has numbers on it or not. So we can factor the 4 out. Still have the 1 on top, so it's 1 over x. And then when we integrate 1 over x, that's our special natural log of x. So we got 4 times the natural log of the absolute value of x. Don't forget this absolute value because if you need to plug in a negative number, it'll correct it and make it positive. Okay, so we got to make sure we do that. We've integrated. We don't need our plus t because of the definite integral, the numbers. Instead, we do our evaluation bar. So we got 4 times the natural log of x. Because I don't have multiple terms here, I'm not going to use parentheses. I'm just going to leave it like this. And then I'm going to plug in exactly like before. Plug in the top, subtract, and plug in the bottom. Right, now keep in mind when you have this number over here, it's part of the term, so you plug in or you use it for each part. You don't just leave it out front or on the first one. So the 4 must go on the same on the part. It's like having 4 times x. You wouldn't put just 4x in the front one and then x in the second one. That's not what we did above. That's not what we're doing now. All right, so this isn't a wrong answer, but if you mess up at one stage here, yes, it is a short problem. You might not see that your answer looks like this. And if you don't see that your answer looks like this, it's because what they did is they used some log rules to simplify it. So this is an okay answer. You might want to get rid of the absolute values first because that's easy to do. But if you don't do anything beyond that step, you'd be okay. What I'm doing here, I'm going to go through the entire simplification because if you don't do that, you get it wrong, you might think your answer is totally off. But first, I'm just going to get rid of the absolute values because they're both positive numbers inside, so they won't change. And now, how do you simplify this? Well, there's 2 ways to do it. The way I recommend, the way integration works is, every single time, no matter what if you have a number up here, like a 12, you'll have a 12 in front because it's going to factor out. So what I'm going to do is factor the 4 out of both. So we get the natural log of 6 minus the natural log of 2 inside. And just factor the 4 out. And then you can combine the 2 logs inside into 1. And we can do that. Subtraction becomes division. Subtraction outside becomes division inside. Okay, so we have the 4 out front. Don't forget that. And then the inside, we got the natural log of 6 divided by 2. 6 divided by 2 is simply 3. So we don't have to mess around with that. I don't need the extra parentheses. I just left it for emphasis, but I don't need the extra parentheses. And now it's actually going to do one more step for your final answer, because what you can do is move this 4 inside the log as a power. Right? Remember, that's another one of our log rules. A number outside can be moved up as a power. As long as it's multiplied. Of course, if we have like a +3 here, that's different. It has to be multiplied. And when we do that, we get the natural log of 3 to the 4th power. 3 to the 4th power is 81. And I do know if when you do this problem, if you get it wrong, it will tell you this is the answer. Like I said, pretty much anything from here to here, any step is correct. But this is the answer you'll see in the homework. So that's one of the nice things about log rules, is that you can make something look a lot more simple. But one thing you don't want to do is type this in your calculator unless it says you can use decimals, and most of them you cannot. Right, because the natural log of 81 is going to be something with a decimal in it. Right, so the next little section, I believe I only have 2 because, yeah, we only have 2 here. Computing definite integrals with substitution. This is really just going to be the same as before when we did substitution, except like you've seen. Okay. Like I mentioned here, when you do substitution, there's 2 ways. I'm going to show you the way that 99% of people like to do it. The book will have both ways, and the homework videos will probably show you both ways as well. The reason I recommend doing the way I'm going to show you, the reason why most people like doing it the way I'm going to show you, is it's just like previous substitution, with the extra step of plugging in at the end. Right, but why do we need substitution here? That's the one thing we remember and want to point out. Well, the reason we want substitution is because we kind of mentioned this before. Think about back in 5.2, when we had something raised to a power that was multiple terms, we didn't want to try to multiply it out and then distribute to be able to use the power rule or all that stuff. So because we have this x squared minus 1 being raised to a large power, we must use substitution. And we use u equals the inside of the power x squared minus 1. Remember, with substitution, you figure out u, but you also need to do the derivative and figure out dx. So du, the derivative of x squared minus 1, 2x, and we multiply by dx. And the way I showed you, the way I'm going to do them every time in this class is divide and get the dx by itself. So dx equals du over 2x. All right, now what we're going to do, just like I did before, is go ahead and plug in. You're not going to do anything differently just because we have numbers on the integral. So we got 0 to 1. The 5x is what we're not adjusting. That's the thing we hope cancels. The x squared minus 1 is our u, what we chose for u, and that's being raised to the 7th power. And then the dx, in place of dx, we're going to put du over 2x. Not du over dx, du over 2x. And just a brief reminder, the key here, when you do substitution method, you should only have u's and du left. So all the x's need to cancel. Right? Like I mentioned before, I'm pretty much doing the problem as if the 0 and 1 weren't there, and we were just doing a 5.2 problem for now. But the x's do cancel, luckily. So what are we left with? We have 5. The x is gone. We have u to the 7th. We have du over 2. We can bring the 5 and the 2 out. And if you're comfortable not needing to actually show this stuff at this point, you've done enough, that's quite all right. The 5 is on top and the 2 is on the bottom, so it's 5 halves u to the 7th du. Now we can integrate this. We have u with just the power and du. So we have 5 over 2. When we integrate u to the 7th, we add 1 to the power over 8, and then we divide by the new power, 8. So this is the one thing that you have to be careful on. When we draw our evaluation bar, these are for the x values, because that's what we started with. All right. Remember, every time we integrated with substitution before, after we integrated, we switched to x, or whatever our starting letter was. And you must still do that. You must switch to x before you plug in. Once again, it's like I'm doing the entire problem without those numbers there until it would normally be done, and then I plug in the numbers. All right, so outside of the u to the 8th here, we have 5 on top and 16 on the bottom. U we have to plug back in as x squared minus 1. That's to the 8th power. And then we have our evaluation bar from 0 to 1. And now we can plug it in. Now we can plug in the evaluation bar. Okay, so we got 5 over 16. Plug in the top number 1. Subtract. Once again, I only have one term here. The part that sort of has 2 terms is already in a parentheses, so I don't need to write an extra parentheses around this. Plug in 0. And then simplify. All right, the first one's pretty easy because if you look at the inside here, we just have 1 minus 1, which is 0. And to the 8th power is still 0. So this whole thing is 0 up front. The second term here, we got 0 minus 1, which is negative 1 inside to the 8th power. All right, so I can drop that 0 in front. We got negative 5 over 16. Negative 1 to an even power is 1. If it was an odd power, it'd be negative 1. We got negative 5 over 16 times 1, which is negative 5 over 16. So that would be this definite integral, negative 5 over 16. Right. Now this is definitely a function. If you tried to graph this and look between 0 and 1, I don't know what it looks like off the top of my head, but you would probably have a hard time being able to tell how, quote unquote, tall the rectangles should be. So our number here may not make a lot of sense if you graph and check, because one rectangle probably won't capture the correct looking answer. So number 2 here, the second one I've got for substitution with this stuff. And this one's also a good reminder of when you use substitution. The other time we use substitution is when the power of e, if we have e to a power, if that power is not just x. Right, but once again, we're going to do the exact same thing from above. We're going to do the entire integral as if the numbers weren't there. Once we get it simplified all the way, then we'll plug in the numbers. But we need substitution for this one. And our substitution u needs to be the negative x squared. It needs to be the power of e. Now we do the derivative. The derivative of negative x squared is negative 2x dx. Then we solve for dx, divide by the negative 2x. I get dx equals du over negative 2x. Right, we're going to go ahead and plug them in exactly like before, exactly like every substitution problem we've done. So 0 to 3. The x in front is the thing we're hoping cancels. We've got e, and then it's our power is what we're using as u. And then dx, we're going to replace by du over negative 2x. Right, now do all the x's cancel? And they do. The x on the bottom and x on the top cancel, which is exactly what we need. So we're left with the integral from 0 to 3. On the inside, we have e to the u times du over negative 2. Right. Now we can bring out the negative 2. Since it's on the bottom, it's going to be a negative 1/2. And the integral of e to the u du is just itself. So we get negative 1/2 e to the u. And now we have our evaluation bar because we've integrated it from 0 to 3. Right. But once again, we cannot plug in yet because the original values were for x and this is u. So we must plug in u equals our negative x squared before evaluating. We have negative 1/2 e to the negative x squared, that's what u is, from 0 to 3. And now we can do it and solve. Plug in our top number, 3, minus, plug in our bottom number, 0. Now keep in mind, because of the minus sign here, when we do minus the negative, we get double minus. But we don't need the parentheses like last time because it's just one term. Right? And what I would recommend here, it depends once again on the direction. Sometimes they want the exact number, which means do not use your calculator. Sometimes they want you to round to a certain point, so just read carefully. But what I would do here is just simplify the exponent first. So here our exponent, negative 3 squared, is negative 9, because this is saying do 3 squared and then put the negative in front. Minus minus becomes a plus 1/2 e to the negative 0 squared, which is 0. Right, now the first thing, unless if you use your calculator, doesn't simplify, and there's really no reason to make the exponent not negative because it's just a number. The second one, since it's e to the 0, that is just 1. Anything to the 0 is 1, so we get just 1/2. And without using a calculator to get a decimal, this is the simplified answer. If you need a decimal in the problem, use a calculator and type that in. Right, but that is kind of every integration thing we will learn. Plugging in numbers, using integration with substitution, and of course, whatever rules go along with it. So as far as the amount of steps, I think for an integration problem, this is probably the maximum we'll see. Right, now the average value of a function, this is something that is pretty important to know if you, once again, if you are going to be in that type of business major where you're going to be using math a lot. And the average value of a function is basically one little extra thing on top of doing the definite integral. So the theorem here says let f be a continuous function on the interval a to b, then the average value of f is given by this formula. Right? There's not typically a common notation for average. Some people use the bar like we did before. I like to write f with subscript avg for average because it's more clear to me. But what this formula is saying is that if you do the definite integral of your function, right, so this is the part we were doing before, and then you divide it by b minus a. So if for our definite integral we want to figure out the average value from 2 to 4, we would do the definite integral from 2 to 4 and then divide by 2. All right, so we compute the definite integral of the function given on the interval, then divide it by the length of the interval, which is b minus a. Right. So I just got one problem here, but it's one of the nicest functions as far as finding the average value because it's easy to graph and see on the calculator. This says find the average value of f of x equals the 4th root of x on the interval 1 to 16. And this is what I'll do. I'll show you in the calculator, then graph the function and its average value on the same window. All right, but the average value means we want to do the definite integral. And let me just scroll up so you can see the formula, be reminded of that. We integrate, or we start by doing 1 over b minus a. Now a is the smaller number and b is the bigger number. So we got 1 over 16 minus 1. Then we integrate from 1 to 16 from a to b, our function, the 4th root of x dx. Right. Now we do need to at least do one thing before we integrate, and that is change this radical to an exponent, because we don't like to try to integrate or do derivatives with radicals. So change the radical to an exponent. And we've gone over this a few times in this class, so I'm not going to go into details, but the 4th root of x is x to the 1/4, right? Because really that is x to the 1 power inside, makes a fraction for our exponent. So all I'm going to do is plug that in, and also might as well simplify 16 minus 1, which is 15. All right, but once you got this set up, even if you're not even any more concerned, what are we actually doing? This is one of the easiest integrals we've done, because you just have to integrate x to the 1/4. What you want to be careful on is just keeping track of everything. We have a 1 over 15 out front. This really isn't any different than when we did any of the other problems, and we factor out the numbers. It just kind of looks like it's already done for us. So think about it like that. Then when we integrate x to the 1/4, we add 1 to the power, which is 5/4. Right? 1 plus 4 is 5. And then we divide by the new power. We didn't use substitution, so don't get confused about that. No, we did not make any substitution. We still have x. But when we write our evaluation bar, we can plug it in right away. Now, what I would recommend is not plugging it in right away and just simplifying this a little bit. And so we got 1 over 15. Now, because we have a fraction on the bottom, we flip it and make multiplication. Keep change flip so that we multiply by 4 over 5. And then we also have this x to the 5/4 from 1 to 16. And then, I'm taking it slow, but you could plug it in right now, or you could have done this in one step. But I'm going to simplify the numbers. The top 1 times 4 is 4. The bottom 15 times 5 is 75. Okay. But this is totally simplified. There's nothing possibly more you could do here. Now I'm going to plug in and evaluate. So we plug in our top number, subtract, plug in our bottom number, and let's do that in the calculator and see what we get, because anytime you deal with fractional exponents, it's always iffy. So we got 4 divided by 75 times 16 raised to the 5 divided by 4. Right? Good habit, if you have a fraction and an exponent, just put in parentheses. Now, if you're worried, this is not going to put the 16 in the denominator, it's in the numerator because the parentheses is not included at the start of the fraction. And I'm going to change it to a fraction, so we get 128 over 75. And then this one we can at least do by hand because 1 to any power is 1. So this is just 4 over 75. And then 128 minus 4 is 124 over 75. So this is the average value. Right, that would be our answer. Now, what I'm going to do is just change that to a decimal so you can kind of see what the decimal is about. It's about 1.65. Right? But what I'm going to do is also do the second part. I'm going to graph the function and its average value on the same window. So I want to graph the 4th root of x. I'm just going to write x raised to the 1/4 because it's the same thing. And then its average value we got to be 124 divided by 75. The window will need adjusting because the x values need to be from 1 to 16. It tells you that exactly. Now the y values, what you can do to figure this out is, what is the 4th root when we plug in 1? Well, it's actually 1. Like if we plug in 1 to the inside, and if we plug in 16, the 4th root of 16 is 2. So you actually only have to have the y values from 1 to 2 to see this. You can make it a little bit bigger, of course. But this is our 4th root function. Okay. And this is the average value. So you can see it's not directly in the middle. You know, if we were looking at the range, it's just from 1 to 2. The average value of that is 1.5. But because it's not a straight line, it has this curvature. I mean, the thing we called it before is concavity, it's curving. But because it's not a straight line, the average value is not as easy as just figuring out the range and doing the average. So it's a little bit bigger than 1.5. It's about 1.65. But that is how we find the average value of a function. Right, so the last thing we'll do here, one word problem with definite integrals. The way the problem is set up, it's usually pretty straightforward that you have to use a definite integral because they'll give you the derivative, they'll give you a range, pretty much everything you'll need. And we'll see how it works. All right, so reading the problem, we'll see why we're going to use a definite integral. This says a company manufactures mountain bikes. The research department produced the marginal cost function, so it's giving us the derivative of the cost right here. And what it's saying is that this is only valid between x is 0 and 900. So whatever happens after 900 is different, but as far as our problem goes, it should only deal with numbers between 0 and 900, where c prime of x is in dollars. I guess I forgot to capitalize that. and X is the number of bikes produced per month. What it wants us to do is compute the increase in costs going from a production level of 450 bikes per month to 900 bikes per month. And there's even a little helpful hint here on what you have to do: set up a definite integral and evaluate it. Now, because of the way you're given the problem, we know we're probably going to integrate the derivative. So let's just set that up and integrate the derivative. Right, now because it's a definite integral, we have to put numbers on it. But what numbers do we put? Well, you have to kind of two places to look at. One guess might be we go from 0 to 900. And the other one might be, well, this says 450 to 900. So maybe we do 450 on the bottom and 900 on the top. Which do we choose? Well, what we're trying to actually figure out as a formula, we want to compute the increase in cost from 450 to 900. Well, you actually are trying to compute C of 900 minus C of 450. Right, so C of 900 would tell us the cost of producing 900 bikes per month. C of 450 would tell us the cost of producing 450 bikes per month. And when we subtract them, that would give us the increase from 450 to 900. Now, the fundamental theorem of calculus says when you want to figure this out, you integrate the derivative. The top number is what's in front, so the 900, and the bottom number is what's behind. So we're used to doing this in reverse. We're used to having the integral given to us. We do the antiderivative. We plug in the top and bottom. But this time we just have to read the question and know which numbers to actually plug in. All right, so it can be a little deceiving because you have two pairs of numbers here. Which one do you use? Well, for this one, we're focused here on the green part. We want to plug in 450 and 900. All right, but once you have the integral set up, let me draw arrows just to make this more clear. Once you have the integral set up, integrate it like we did all the rest of the problems, and then, if you have to interpret the results at the end, we'll do that. Now, this is something we can integrate each part of pretty easily. The integral of 700 is 700x. The integral of x over 3, well, if you want, you can write the over 3 part as 1 over 3. And the integral of x, we add 1 to the power, x squared, and we divide by the new power. And then we put our evaluation bar, 450 to 900. Now, like always, I'm going to just simplify it a little bit if we can, and we can make this x squared over 6. So we got 700x minus x squared over 6. Because we have multiple terms here, I like to put the parentheses like before. Right, so just simplifying in this first step. And now we can do our evaluation. All right, so we plug in our top number, 700 times 900 minus 900 squared over 6. And then our bottom number, 450. 700 times 450 minus 450 squared over 6. And like with the rest of these, the number's pretty big. Let's look at the calculator and do as much at a time as you're comfortable with. So I'm going to do what I did before, do the first thing, 700 times 900 minus 900 squared divided by 6, 495,000, pretty big number. And then the second one we want to replace with 450 to 900. So I'm going to do that. And we got 281,250. And subtraction in between. Then figure out that. So 495,000 minus 281,250. And we have 213,750. That is the increase in cost going from a production level of 450 bikes per month to 900 bikes per month. Right. So, kind of impressive what, think about what we've been doing in this class and now the problems we're doing. We have the derivative, the rate of change of the increase of cost, and we figured out just from the derivative how much the cost would increase if we go from a production level of 450 to 900. Now, of course, we could do from any two numbers here, but as I've been mentioning in this chapter, when we do word problems in it, this is not an uncommon practice to figure out the derivative in the background and actually compute stuff from it by doing integrals. But this is, for most of applications, this is a more realistic application than the other one, because you're usually going to want to figure out the increase or decrease or whatever it is over a range of two numbers like this. So I would say, as far as almost every problem we've done in this class, especially in chapter 5, this is the most relevant one. Right, but that's using a definite integral and a word problem. The same key points here point to integration because we're given the derivative. We want to figure out the original. But you just want to notice here why we're doing a definite integral is because we want to figure out the increase. It could have been decrease as well of what happens when we change the production levels. But that is it for this section.